we welcome Dimitri and Emile to talk about evaluating process-level power models and the deep question of energy consumption of an application. And I think I need to leave you the floor now. So I'm going to stop presenting.
Okay, can you hear me?
Loud and clear.
Okay. Alors, comment I'm looking. How can I share my screen? Okay, this one. Pop. Okay. So can you see my screen?
Yes.
Yes, all good.
Yes. Okay, it works. Okay, thank you. So hi everyone. So I'm with my colleague Emile. We're both working at the company Davidson Consulting. And today we are going to talk about some research activity, what we've done on process level power models. So we are going to explain what we mean by process level power models. So it's a research activity that has been published in a conference called Cluster, and yeah. So I think we think it can be interesting for people at Boavizta. So it's a presentation a tiny bit technical, but I do my best to explain it as best I can. So maybe a bit of context. So here we are interested in reducing the energy consumption of ICT, and nowadays a lot of people want to measure the energy consumption of their software. So it's interesting to ask the question why do we want to measure the energy consumption of softwares? Basically, the train of thought is that software are run on servers. Servers consume energy, and we want to reduce the energy usage of servers. So basically, an hypothesis is that measuring the energy consumption of softwares should give us insights on how to reduce this energy consumption. And so reducing the energy consumption of software should help us to reduce the amount of energy consumed by server. So it's important to have this in mind, because we'll go back to this issue at the end of the presentation. So that's the main reason why people want to measure the energy consumption of their software. So how can we do that? So if you've seen the presentation 2 weeks ago, it's a bit familiar. How can we measure the consumption of a software? So today we have two main approaches. So we can do it at the server level or at the process level. So at the server level, basically you just need to buy a sensor, for example. So a smart PDU that you can plug on the energy electric outlet to measure the energy consumption of your server. So that's the reference value. That's a physical measurement. That's very reliable, but you need to buy it. Or you can use embedded sensors that are included in most modern processors, such as Intel Ripple. So in both cases, measurements are considered reliable, even in the case of Intel Ripple. But it's a bit low level, so you need to measure either the whole server or the whole CPU. You may need to buy several smart PDU if you want to have the measurement at the whole server, but you cannot have the measurement at the service level. So, for example, if your server is running many different applications, you cannot have a measurement per application. So in order to face this issue, there's a small ecosystem of software sensors that have emerged. So the principle is kind of always the same. You take the energy consumption of your server and you split it among the different services or software you're interested in. So it should give you a measurement per process, and it's based on custom models that are currently unevaluated. So we are going to discuss about this. and about the discussion about the issue of how can we divide the energy consumption among processes. So I talk about this software as a small ecosystem. So here I gave a few examples. So for example, Power API would have been created by INRIA, Scaphandre, that most people should know here, Kepler, and Power Joulard that have been presented last 2 weeks ago. So there's different allocation keys, so different way to split the energy consumption, but it's always the same ID, general ID. So for example, Scaphandre and Power Joulard uses CPU time ratio. So if your application is running twice longer than another application, then it will be attributed twice the amount of energy consumption. For Power API, it's a bit more complex. There's a bit of machine learning involved, but the idea is kind of the same. These models, they provide different results, different estimation, and here we were interested at the beginning of our research on how can we compare the different measurements given by the different models. In particular, for example, how can we say if a model is good or bad, and how can we say, for example, if, I don't know, Scaphandre, is it better than Power API, or Power API, is it better than Scaphandre? That was the question we are thinking about at the beginning of our research. So usually, the argument we face when we want to work on, when we ask ourselves why those models were not evaluated. So usually the answer is there is no baseline. If you want to model, for example, the energy consumption of a server, you have baseline. You need to buy the physical energy sensor, and you have a physical measurement to compare your model if you want to measure the whole server. But here you cannot have a physical measurement to validate or invalidate your model. So there's no reference value, and we think that if we have no reference value, it's because we didn't take time to define what do we mean by energy consumption of a server. And we are going to see in this presentation that the answer is not straightforward, it's not trivial at all. And in the context of server running different applications at the same time, like for example in the cloud or on your laptop, or most cases, you have plenty of applications running on one physical server. We are going to see that the concept of energy consumption of a server is not as straightforward as we can think about. So first thing first, how do physical servers generate energy consumption? So this is a bit technical, so I did some terminology recap. So we are going to use a bit of technical terms. So just a few explanations. So I'm going to talk about CPU cores. So one CPU, which is the main unit that does all the computation in your server. One CPU is composed of several units working simultaneously. Those units are called cores. So it's a sub-part of the CPU that works at the same time. I'm going to talk about process threads. So usually software are built as a sub-program called threads, and those threads can be executed on different CPU core. So it's interesting. Usually, yes, your program can be executed, sub-parts of your program can be executed in parallel. And I'm going to talk about hyperthreading and turbo boost. So that's quite technical, but basically it's mechanisms that are built into your processors. And those mechanisms can allow your processor to adjust its energy consumption depending on its load. So basically, modern processors, when they don't have any load, they can sleep. And when they have a big load, they can wake up and go as fast as they can to turn back to sleep when the load is finished. So how can we measure the energy consumption of a software, and how can we model this energy consumption? So we took several programs what we call stress functions. So it's basically software that does one thing very constantly. At the same load, we can configure it. It's super stable, and it's convenient to reduce the variability in the measurements. So here, for example, the blue curve here, it's the energy consumption on a server while executing one of our stress functions called the Ackermann. So we see that it starts and it's very stable. It does always the same thing, and then it shuts down and it's finished. So that's quite convenient to measure at a given stable load. We use two servers, one small server, which is basically a refurbished desktop computer, and one big server, which is more representative of real-world server that can be used to run inside the data centers. So, first thing first, we turned off. We start in the easy case. We turn off all the optimization that let the processor to adjust itself depending on the load and so on, and adjust its energy consumption. Here we turn off hyperthreading and turbo boost. So that's the easy case. And we take our servers, we generate different load going from no core activated, so the server is quite sleeping, to all the cores activated, so the server is running at full speed and full activity. Here, the two curves on the bottom are the energy consumption we observe with the small server, and the curves above are the one we observe on the big server. So, and the blue one is the minimum value observed because we run different programs, and the red one is the maximum value we observed on the server. So basically, different loads on the server, different program, and we can measure the evolution depending on the load. So what can we observe? There's several interesting things to observe. So for example, for the same CPU load, we have very high variability. So for example, when we have a server that is running at full load, full speed, depending on what is being executed on the server, we have very different measurements in energy consumption. So for example, on our big server, if we are doing random number generation, actually it's a bit cheap to compute. So you will run at 185 watts. But if you are doing products of matrix, which is quite energy intensive, you will run at 210 watts. So there's 12% of differences in the energy consumption. So we have very high variability. So you cannot just, it's important to know what is running on the server to be able to model the energy consumption of server. So that's something that is usually not very known. The energy consumption depends on what is being done, not just on how much the server is being loaded. And another interesting thing is that if we take a lot of, let's say we took our 12 programs and we want to compare the energy consumption of all the programs to be able to say, okay, this program is the most energy intensive and this one is the cheapest one. Actually, if you're doing the classement, the ordering, let's say, the orders will depend on the physical machine. So for example, the most expensive program regarding energy consumption on the big server is the one which is doing products of matrix multiplications, and on the small server, the most expensive one is the one that is doing computation and float, which is the numbers with decimal values. So that's important to know if you are doing modeling and estimation of the energy consumption of, for example, two applications. This result will depend on which server you are running. So you cannot say in absolute truth, okay, this program is more expensive regarding energy consumption than this other one, because it will depend on which server you've been executing the applications. Another interesting part is that there's different steps in the energy consumption. So when no program is running, we call this idle. So the server is sleeping. Here, for example, the big server, when sleeping, is consuming 21 watts. when we start our first program using one core, there's a jump in the energy consumption because the CPU is waking up. It wakes up and it wakes up at 110 watts, and then since this part, starting at one core, when we go to all the cores, to loading all the units in the processor, you will see a, let's say, linear energy consumption that depends on the activity. So here we are doing the difference between the part going from 0 to 1, and then the CPU is woke up, and then it's quite linear from 1 to all the cores being loaded. Okay, so this is how a simple server can generate load, depending on the activity, energy load. So if we go back to our issue of energy measurement, we can ask ourselves, how can we define the concept of energy consumption of an application? What do we mean by energy consumption of a software? So one first definition we came up and we considered that one simple definition is that we can consider that the energy consumption of an application is the consumption that would have not been observed if the application has not been executed. So for example, let's say we have a server with plenty of applications running. We take the measurements and then we remove our application from this server. We take another measurement, and if we subtract the differences, we can say, okay, this is the energy consumption of my application. So for example, to give numbers, let's say your server is running at 110 watts, for example. You remove your application, now it's at 100. So we can say, okay, so my application is consuming 10 watts. I need 10 watts to run my application. As we said before, the energy consumption in our cases were split in two parts. One part going from 0 to 1, that is not depending on the load, but that is just here to wake up the CPU, and one part of the energy consumption that is depending on the activity. So we can say, okay, there's this part in light red, light orange, that is just the energy consumed by the CPU to just be wake up, and here blue and the red and the green part, that is just the energy consumption that is depending on the load. So the more things you do on the server, the higher it will be. So first thing, first issue that we can have is how can we split this energy consumption among the different processes? Should we just ignore this part? It's like the same issue with the idle energy consumption. Should we ignore this part? Should we give it depending on how much dynamic activity your application is doing? It's not that straightforward. We can see that we can have different answers. We can maybe disagree on how we can do it. And we see that here we can take a decision that is not linked with the physical reality. It's just a decision that we can take. So yes, we can take this decision. So we could just say that we could remove this part and just focus on the dynamic part that depends on the energy consumption, on the load on the server. We can say, okay, we're just interested in the dynamic load. However, this part here that goes from 0 to 1, that we call the residual energy consumption, it depends on the speed of the CPU. So the more activity the CPU is doing, the higher the frequency of your processor, the most energy it will consume just by existing and just by being woke up. Actually, when you create programs, different programs can be executed at different speed. So, for example, if you have a program that is waiting a lot, for example, it's reading files, it's waiting for user input, it's waiting for network messages on the network. When your program is waiting, then the core, the server executing the program will execute it at very slow speed. But if your program is not waiting at all, just it can go as fast as it can, then the processor will go as fast as it can. So different program will be executed at different speed. So now we have an issue. For example, if we take two applications, the blue one and the green one, the blue one is running at low speed, for example, because it reads from files, it waits for I don't know, network activity and so on. And the blue one can go super fast because maybe it has no wait at all. When we run independently, so first the blue, and then when the blue is finished, we can run the green one. At the blue one, the processor will go super slow, and then at the green one, it will go faster, so consuming more energy. So now, if we take both and we execute both, for example, you're on the cloud, for example, if you're executing both applications, the server will go fast because the green one needs the server to go fast, and it will generate more energy consumption that we add if we just take the blue one. So for example, so what I mean by this is that the blue application is not responsible for the speed, and the green one is the application responsible for the speed. So here, for example, if we could end up attributing more energy on the blue application when both applications are running in parallel than if we just run the application separately. So here, what I want to say is that the application is depending on the context. The energy induced by executing the blue application is not just depending on the blue application, what it does, but also depending on what is the current state of the server, what is running on the server. And that's the main issue we are going to face in this presentation. So it already seems quite complicated, but actually it's the easy case. On real-world servers you can find in data centers, actually we have mechanisms I talked before called hyperthreading and turbo boost that enable the server to run at different speed depending on the load. And turning off and on different subcomponents. So usually when you have no load on a real-world server, the server will turn off several of its components to reduce the energy consumption, and that's a good thing. And modern servers with those mechanisms can run a significant amount of application in parallel, more than you could use on without those mechanisms. So when we turn on those mechanisms, the energy curve goes from this linear thing to a logarithmic energy consumption. So here, the energy goes from 0 to 1 core. So that's the same thing we had before. And then it goes, and then it nearly reaches a plateau. So modern servers are more energy efficient than when they are fully loaded than when they are quite empty. It's quite easy to see. For example, let's say that I start a software that will go from 0 to 20, but increase the percentage of cores by 20%, for example. Here, if we go from 0 to 20, we'll go from, I don't know, 100 and let's say, okay, 110 to nearly 200. So, okay, nearly 100 watts. But here, if we are on 80%, already loaded at 80%, if we add our application that adds 20% more load on the processor, we'll go, okay, we will have nearly no differences in the energy consumption. So that's an important fact. Servers are more energy efficient at high load, and when you add a new software to be executed on a highly loaded server, you won't bring as much energy as if you are starting your service when the server was empty loaded. So here, as I said, the residual consumption is still present, and we have a logarithmic curve. and we still have differences between the cheapest program and the most expensive program. So now, as I said, it makes things more complicated because before you could use take the, for example, if you have two programs, the blue and the green one. Before you could take the energy consumed when by the blue application when it was running alone. You could take the green energy consumption of the green application when it was running alone, and you could sum it, and you could have the energy consumption when running both applications at the same time. Here, it's not the case anymore. So for example, here, if you run, on the one hand, if you run the blue application alone, you take the energy consumption, you take the green application alone, you take the energy consumption, and then on the other hand, you execute both applications at the same time. Actually, running both applications at the same time will result in less energy consumption. It costs less to execute both applications at the same time than running one first and then another after the first one. So that's why those mechanisms are interesting, because we want to be able to consume less energy, but it makes things more complicated in the modeling of the energy consumption. So there's a question, monolithic application use less energy than microservices. That's a tricky question. So actually, if you deploy, it's difficult to say if you deploy all the application on the same server. If you run all your services on the same server, you could think about your different services at the same same application. But if the question is on one case you have one server running one monolith application at 100%, for example, it's super loaded. Yes, it will consume less energy. For example, two servers running two microservices at 50% of load. If it's the question, that's the answer. So there's value in putting all the services in the same server if it can help you to turn off the servers. So you could say, okay, that's just the issue of modeling. Why do I care about this? What's the impact on my observations? And this is the impact of you will have. I will come up later with real-world values. So, for example, we take a server in the cloud. The server will be running three applications: a green one that is running during all the experiment, a red one that is running first, and then a blue one that is coming later. So first, we are in the situation where we have two applications, red and green. They both consume the same energy. So here, let's say a bit more than 20, let's say 21, both 21 energy consumption, 21 watts. Then the red application is turning off. What I will observe is that as the server is more efficient at high load, I will observe a spike in the energy consumption of the green application. Does it mean that the green application is doing something more? No. It just means that it's now running on a less energy efficient server because the red application is leaving. And then when the blue application is running, starts, I will see a decrease in the energy consumption of the green application. So does it mean that the green application is now doing less work? Absolutely not. It just means that now the green application is running on a more energy efficient server because of the arrival of the blue application. So that's important to see, that we can see spikes, and that's something we can confirm with real-world experiments. We see spikes that are not linked at all due to the differences in the behavior of the application, but just because of the change in the context. So to summarize, we have a lot of issues with modeling the energy consumption of a server. So first, it's really tricky to measure to model the energy consumption of a server. There's for example, even at a given load, even at full load, you can still have high differences between the case where the application, the server is running one type of application or the server is running another type of application. So we need to have, if you want to model the energy consumption of a server, you need to have a deep level of insights on what is going on inside the application, and usually you need a level of insight that is not very possible to attain nowadays. So it's very tricky to model the energy consumption of a server in a way that is can be used for to provide the model that can be used for every kind of application. So that's the first part. So it's technical aspect. Then the second part, depending on where you are executing the application on the curve, you will have different kind of energy consumption. So if you, as I said, if you start your application when the server is empty, it will create more energy load than if you start your application when the server is fully loaded. So it can be tricky. For example, let's say you run your application twice. First, an old version of your application first, and then you create some energy optimization, and then you run the new version of the server. How can you say that the new version of your application is more efficient if actually the energy consumption depend on what is happening on the server? It's a bit tricky. And then yes, it's all other problems, like for example, what should we do about the residual consumption that just exists here because the server is waking up? And what we do with how can we allocate the decrease in energy consumption because of the increase of efficiency. It seems that we have both technical problems that can be solved with more details in the model, but also we have issues that are not technical and will be here even if you change the model. Here, for example, you cannot do anything to change the fact that a server is more energy efficient at high load. So evaluation. So we took back our experiments, and now we wanted to run the experiments on two models, Scaphandre, that you may know, and Power API, which is basically like Scaphandre, but the difference between both is that Scaphandre is giving energy consumption depending on CPU time, and Power API has a bit more complex model with some machine learning. I won't go too much into details, except if you have questions about it, but it's a bit more complicated model with machine learning. So first, we have no hyperthreading, no turbo boost. So we go back to the simple case where the energy consumption was quite linear. And here we are comparing, the differences in energy consumption on the first case called the sequential case, the case where we execute two applications. So first, let's say we take two applications. On sequential, we executed the first one alone, and then when the first one is finished, we execute the second one alone. So that's what we call sequential. And then what we call by parallel is that we take the two applications and we run both applications at the same time, and we ask our models what is the difference between both applications regarding energy consumption. So each point here in the graph is an experiment done comparing two applications. And what we would like to expect is that the ratio, the difference in energy consumption when we run both applications alone, should be the same that ratio when we have two applications running at the same time. So I want to be able to say that my first application is consuming twice more energy, and this twice more energy than the other one should be independent of the fact that if both applications are running at the same time or independently. And here we take three cases, the blue one, just to create more cases to compare. We have the first, the blue dots are when both applications use one core. The green, it's when the orange is when both applications uses two cores, and the brown one is when both application uses 3 cores. So same application, but different sizes. They both have the same size, but in one case, both are bigger than the other case. And what can we see from this graph? It's complicated, but it's actually easy to understand. Is that when we run both applications in sequential, so first the first one and then the second one, we can see a high range of energy consumption. For example, here, 60%, it means that the first application consumes 60% more than the second one. Here, for minus 40, it means the second application is consuming 40% more energy consumption. So when we run the application alone, we can see the differences in energy consumption. But when we run both applications at the same time, we can't see anymore the differences in energy consumption. It's all on 0. That's interesting. We can see the differences in energy consumption. And when we take the second graph, and the first graph, all applications at the same size. So for example, here we are comparing application on 1 core versus application on 1 core. Here we are comparing application on 1 core versus application on 3 cores, 1 core versus 2 cores, 2 cores versus 3 cores. And here we see 3 different plateaus. And that means that the model are able to say that, okay, if you're using more core, you will be using more energy. If you are using less cores, you are using less energy. But if both applications are using the same number of cores, the models can't see the difference in energy consumption. So here it's for Power API. Here it's for Scaphandre. Scaphandre is a bit more able to see the difference, but still we still have the 3 plateau. So yes, the Scaphandre is, let's say, a tiny bit more able to see the difference. If both applications, for example, are only on 1 core, Scaphandre is a bit more able to see the difference in energy consumption. But let's say that usually both models can just say that, okay, if you're using twice the number of cores, you will be using twice the energy. Here it's so the first case was on the small server, and now it's on the big server. And the big server with Power API, it's a bit more chaotic. Let's say it's quite chaotic actually. We've estimated the energy difference at 1000%. Actually, the issue we have with Power API is that Power API is not deterministic. So Power API can give different estimation even with the same context. So for example, here is the detail of one experiment. 2 runs of the same experiment. We are looking at the difference between Float64, Matrix Prod, so 2 different programs. So here, Matrix Prod is the red, Float, so okay, you have the red program and the blue program. Here, Power API in the first one is saying that Matrix Prod is far more expensive than Float64. And if you just run the second time the experiments, Power API will go to the conclusion that Float64 is using more energy than Matrix Prod. So actually the contrary of the first experiment. No differences in the context. We just run twice. It's because there's a learning phase and it's using machine learning, and machine learning can sometimes give different results because of machine learning. So in Scaphandre does not have this issue because Scaphandre does not use any kind of machine learning. It's a more simple model, so it's more stable. And Scaphandre here we can still see the plateau, and so it's we can see a bit of differences between the consumption of different applications running at the same number of cores, but still we can see less differences in energy consumption, but we can observe if applications are running alone. And here we have 2 plateaus and not 3. The difference is because here, for example, here we have the ratio of 1 versus 3, 1 versus 2, 2 versus 3. Here, 4 versus 8, there's a factor of 2. 8 versus 16 there's a factor of 2, and here 4 versus 16 there's a different factor. So yes, you can see 2 plateaus, but it's just because of the choices we made in the different sizes of application. Here we still have the same observation, but we can just say that, okay, if your application is using twice more cores, twice more energy, but we cannot go further. So it was, again, it looks complicated, but it was actually a super simple case. Here, all the applications are running at the same speed. But now, if we manually change the speed on which of the different application, when we can move we can see differences in estimation because we manually change the speed of the cores. Because as I was saying at the beginning of the presentation, the speed of the cores will actually influence the speed of the amount of energy consumed by the CPU. So before we could say, okay, we can see the difference, but at least it's centered on the curve, so not bad. Here it's not even centered on the curve. So the difference in what I want to say by this is that the difference in speed, in execution speed, will have a high impact on the energy consumption. That's something usually you can't really control. So here it was experiments presented with stress application. So you can say that stress applications are not used in real-world application. It's not real-world application. We want to see how can those models behave with real-world application. So we took 4 softwares. Here, description of the software. We chose the software. It's come from a test suite called the Fornix. It's a benchmarking test suite. We took 4 softwares. We chose the software because they had good reproducibility. If you run, I don't know, 10 times those softwares, you will have always the same energy consumption. So it's important for the experiments. And we took different kind of software. So you have physics simulation, 7-zip, so it's compress and decompress files, compilation in C++, and one benchmark in Java. So it's closer to real-world application. And here is the energy consumption of those applications. So those applications, they have a beginning, a start, and an end. They do a fixed load. They do other activities. And here is the energy profile of the server when you are running the application alone. So it's interesting to understand how those applications behave. So for example, here, compress 7-zip, we have a series of, let's say, 10 plateaus. Build 2, you have 2 big plateaus with a spike between, a decrease in the load in between. Cloverleaf, you have 4 big plateaus. And Dacapo, it's a bit more chaotic. Dacapo is a lot of spikes. So this is how the application behave when they are alone. So here the energy consumption is completely representative of the load of the application. So what happens when we run both applications, if we take 2 applications and running at the same time? Here we are interested in running build 2 and Dacapo at the same time. So let's remember Dacapo is the one with a lot of spikes, but quite chaotic, and build 2 is 2 plateaus with a decrease in the load in between. Here is the energy consumption estimated by Power API on the left and Scaffold on the right for both applications. Build 2 in orange and Dacapo in blue. We see that more now the plateaux are less easy to see. It's a bit more tricky now to understand the behavior of the application. Here the plateaux were quite stable. Here we have a lot of series of spikes that go up and down. And actually, if those spikes go up and down, it's because here if we have spikes going down, it's because Dacapo is executing its spike. And when Dacapo finish executing its spike, so now it's turned off, the energy consumption will go back again. So remember, it's when I was saying this part, if you remember this slide, we see the real world effect of this slide. And we see that now we have spikes going up and down, not because of the activity of the application. If you take CPU time, for example, you don't have this impact in CPU time. You don't have the spikes in CPU time. And so is a test run on Scaphandor 5 or less? Good question. I think we need to go back to the paper I think we wrote on the paper which version. We ran it in 2023. No, en 2023. So maybe it's not the less recent Scaphandor version. But still here, we have the same observation on Power API and Scaphandor. We have the same impact that the behavior of the energy consumption does not follow the behavior of the application. And here, with compressed 7-zip and Cloverleaf, so Cloverleaf 4 plateau and compressed 7-zip, let's say 10 plateaus. And here we have a difference in between Power API and Scaphandor. The behavior of Power API is a bit chaotic at the beginning because remember there's a learning phase, and it's a bit more stable here with Scaphandor. The model is coherent. But here we have spikes on the Cloverleaf, but we can just explain because there's a drop in the energy consumption of contract 7-zip. Yes, maybe we could rerun on the 1.0 version, but I don't think it...
Yes, I think we did run that on the last version. It does not depend on the version. It's
because it's a way the server, but we need to be exact on the version. We need to have a look at the paper again. But these impact here are because of the way all the things I was explaining before, the way a server is more efficient at high speed than lower speed. So here we have spikes that are you cannot explain the spike because of the activity on the application, and you need to have a understanding on the whole context of the server. So, okay, so you can say that, okay, the behavior of the application is changing, but at least maybe it's consuming the same number of energy in joule, the same amount of energy in joule. Maybe the watts, it's chaotic, but maybe the joule is the same. And actually it is not. So we observed a variation in, for example, in Cloverleaf on the small server. We observed 23% variability when executing the application with different application against in parallel. And on the big server, actually on the big server, we observed 55% of variation, because the bigger the machine, the bigger the effect will have, because it consumes more energy, obviously. And here we have 43 kilojoule of differences, and actually 43 kilojoule is more than 26 kilojoule, which was the amount of energy observed, the minimum amount of energy observed for the application. So we have a variability that is higher than the energy consumption of the application when running observed at the minimum. So what I want to say is that it's not just a I don't know, pedantic observation. It has important impact on the estimated energy consumption. So conclusion. So what do we know? It's important because this presentation, there's a lot of things that we don't know. But what do we know now? A server is more energy efficient at high load. Modern servers are more energy efficient when they are fully loaded. So ideally, a server should either be running at maximum capacity, so maximum efficiency, or being turned off. So obviously, when we turn off and on again a server, it consumes energy. So it's a bit simplification, but there's value in trying to, when you have a fixed amount of tasks to do, there's value in trying to execute those tasks as quick as possible to be able to turn off the server. So you will have this energy efficiency when running the server at high capacity. So another conclusion that we make, if we believe that we need, and actually we can evaluate those models. It's not easy, but we need to be able to evaluate those models. So even in the scientific literatures, so for example, Power API, I think we can talk about Power API because we are part of a consortium of Power API, so let's say we can. It's not unfair to talk about Power API. Even for models in the scientific literatures, there's no real evaluation of those models. Those models give estimation, and they don't really evaluate with estimation. And as we saw today, it's not that straightforward. And usually, those models, when we look at it, they behave in a way that is not intuitive at all for us. So, for example, we would expect those models to give energy that is linked to that is representative of what the application is doing. So, for example, if I do energy optimization in my application, I would expect to see an application that consumes less energy, but actually it does not. It depends also on the context. For example, if I take two applications, I would expect to be able to do the sum of their energy consumption and get the energy consumption by server. Actually, it's not that easy. So yeah, that's one of the key facts here that is important, that those models behave in a way that is actually not that intuitive for us humans. So we believe that we need to be able to evaluate those models, and it's not that easy. Yes. We presented some issue with those models. Mainly the biggest issue is that the behavior of an application, when we look at their energy consumption through the lens of the models, the energy consumption estimated is more linked. It's actually quite a lot linked to the context. And actually sometimes it's more linked to the context than on the application itself. And we believe that this issue is inherent. It's because of the energy consumption of the server, and it's not because of the model. If we try to look at different models, and it's just because a server is more efficient at high speed, a higher level than at high consumption than on low consumption. So actually, we believe that changing the model, it's not an issue of accuracy. It's an issue of how the server is behaving. So yes, so the energy induced by the execution of the server does not only depend on the server, but also on the it does not only depend on the server and the software. It's also depending on what the server is doing. So I try to do a parallel with life cycle assessment. Maybe it's not very good parallel because I'm not expert on life cycle assessment, but from what I understand, usually it's quite admitted that you can't compare two different life cycle assessments because there's potential differences in assumptions, input data, scopes, and so on. And actually what we can observe is that process level energy models have the same issue, because here the scope is not only the server, the scope is also all the application running on the server, that is not your own application. So actually the context is actually changing. If you run your application twice, the context will have changed, and actually we can even say that the context is changing every second, because every second there may be a new application coming or leaving or different in load on the application. For example, if one application now suddenly have a spike in energy consumption, the context is changing. So actually the context is changing every second. So that's issue. And if we circle back to our main problem on why we want to measure the energy consumption, so this is our take, let's say, that results of these observations. This is what we think. Maybe we are wrong, but we believe that if if we measure the energy consumption of the software, it's not just to produce numbers, data, and so on. It's to find leverage to reduce this consumption. We want to reduce the energy consumption of ICT, and yes, as this is a very important matter. However, it seems that this consumption estimated by the models depend more on things you can't control, such as the execution context, than on things you can control, optimization. You can control the optimization. You can control what your application is doing, let's say by reprogramming the application, but you can't really control where your application will be executed on the cloud, or you can't control the application managed by other clients, for example, of the cloud. To have perfect control, you will need to execute every application on a different server. Okay, maybe. But here, as we saw, there's plenty of value in trying to execute as much application as possible on a low number of servers. We talked about the energy consumption. It makes sense for energy consumption. It also makes sense in the, producing new server. It costs a lot of resources. So we want to also reduce the amount of servers we buy. So what do we do? What can we do from that? This is our belief. Maybe we may be wrong. We believe that the issue of energy consumption should stay at the server level. There's still a lot of value in understanding how the server works. There's plenty of value in that. For example, here we can say that servers are more energy efficient at high load. And if you are managing a cloud, you can do things to run your server at high load and then turning off the servers and so on. So there's still plenty of. We are not saying that we should stop thinking about energy consumption. We are not saying this at all. We are just saying that maybe it doesn't really make sense to try to go from the physical realm of the energy consumption of the server back to the, let's say, numerical realm of the application. And we are also not saying that there's nothing to do on the software level, not at all. We believe that on the software level, we should focus on using less server. So as an impact, it should lead to less energy consumption. And we already have actionable metrics for this, coming from the traditional performance analysis way to do things. For example, measuring CPU time, memory, and so on. So that's one of the observations. I would understand that it's maybe a bit controversial. So yes, it's just there's value in working on energy consumption. Yeah, we are plenty agree on this, but we are a bit skeptical on the way we want to model the energy consumption of each application because of the way it behaves on the server. So I think it's all it's finished for the application. So yes, it was another slide. So okay. Usually there's a difference in the goals. If you want to do optimization, you need reproducibility. If you want to do optimizations of optimization, it's hard to have reproducibility with models. Maybe it works if you want an abstract cost, but take into account the execution context. For example, when you want to do lifecycle assessment, we're not expert in this topic, but maybe it makes sense. It makes sense to actually be able to capture the environment context. But if you want to do optimization, we believe it's a bit more tricky because the way it depends on the context. Okay. So that's it. We took quite a bit of time. So if you have any questions, remarks, things you disagree on, things you have questions on, we will be really happy to answer the questions.
I will start. François Mariami speaking. Hello. Thank you for the job on the presentation. I was quite confused by the fact that you use the word energy almost all the time, but your curves are
yes, it's for.
So it's wow. I was very mixed almost all the presentation because
yes.
at all, and you can have an higher power and a lower energy, or the same software can have an higher power profile but a less energy consumption. You have to integrate the time to be sure that we are in the right direction. I think we had to focus on energy and not on power. But power is very important to measure because we are only measuring power and not energy for sure. And I was quite confused by these slides.
Yes.
It is exactly the same software with the same task that is running on the two servers.
Yes. So it's we have those applications that are quite reproducible. When you execute the application alone, you have the same energy and the same profile in power. And when you run the application with other applications, the models, now we talk about the models, they give different estimation in the energy. So what we wanted to say that we have differences in the power, different power profile, but also in the energy consumption here in kilojoule. So we have a variation in the energy estimation.
And it is the context of there is several applications running on the same server?
It's because the server is more efficient at high load. So actually, if you, as I was saying before, if you take two applications, it will lead to less energy. If you run both applications at the same time, than if you do the sum of the energy of each application run independently. So that's why we see differences. Yeah.
Okay, and another thing I don't understand is this strong variation of on one specific server, you have the strong variation of energy, and as you don't have a strong variation in power, as I think in your power profile of the runs of your application. So
yes, you have the same observation on the power profile because here in this experiment, the application we run used 6 of the 12 cores available, and it is the same on the second machine. And here we have relatively that example. Here we can see that the application, when running in parallel with another application, is consuming about 40 watts per second. When it was running alone, it's about 80. So we can see the difference in terms of power and in terms of energy consumption. I don't know if that answers the question.
Difficult for me to find, in fact, the relevant rules at the end. What do you have to do for a specific software? Anyway, what is sure is that in the multi-core context and in a shared context, especially in the cloud, it's more difficult to understand where we are and when we have to go, for sure. But what we need is clear understanding. It's clear recommendation for software developers and especially for architects. Do we have to use big servers, shared big server, and do we have to use smaller servers? And you have spoken about the allocation of the I don't know how to say that, the static power, and the fact that when you start a power, you have almost 200 watts running without no application running. So this fact of using this, the way you allocate this dead power, I don't know how to say it, static power or idle power, the way to allocate it during the runs of your application is very important because I think it changes the result you have at the end.
I don't think we need to do allocation for that, because if we take the energy consumption of the servers alone, we say I have two servers, one big and one small. I'm running my applications on them. I take the consumption of the servers, not the applications, the servers, and I observe the energy consumption, and then I know if my placement is good or not. So if I have a cluster of big machine and a cluster of small machines, if I take the consumption of the clusters, I will have the answer to that question, and we don't need to do some repetition of energy consumption between the applications. So if for the developers, I don't think that's an important question to ask to ourselves. If we the question we might need to answer is how much CPU usage I'm producing, how much memory usage, memory space I need to run my application, because that will have an impact on the placement. But the placement itself, it's not your responsibility, it's the responsibility of the cloud provider or
sysadmin.
Yes. So the smaller your application, the better the placement will be. That's something we can know. If you have small applications, it will be easy to deploy on servers. It does not depend on what kind of server you have. But if you have only big application, you will need to have big servers. But if you have small applications, the fact you have big or small servers, that becomes the responsibility of the cloud provider.
Yes or no? There is a discourse of the cloud providers to share to distinguish their responsibility from our responsibility, but as an architect, between the cloud provider and the software developers, there is the architect, and most of the time it is from the customer side, and he has a role to play.
Yes, what I mean is, if your application is small, it will be easy to.
I have to do the timekeeper here. That's a very interesting discussion, but maybe we can keep on the discussion on Mattermost. But there were an important question from the people taking notes that they took some screenshots. And are you okay to have this?
Yes, we are. Thank you for the. Thank you, Simon. Yes, it's okay for us to screenshot. Okay. We will share the also.
And there is a paper if you want more details.
Yes. I will include the link to the paper on the slides also when we share the slides.
Oh, okay. Super.
Gael, I think we can let the meeting run if Absolutely. Some people can stay, want to discuss that, and if Dimitri and his mate can stay there, maybe we can keep discussing. And for the people who cannot stay, they will be able to watch the recording. Yeah.
Okay.
Yes. Okay.
So bye everyone who needs to leave, and let's have the discussion rolling out.
So to go back to François. Yes, sometimes it's difficult to say which person has which responsibility, but we can still have a clear recommendation, I believe. Well, Benoît.
Yes, thank you for the presentation and your work. To jump on what François said, and maybe it really depends on the role you play in the value chain. And to clarify a bit, the scaffold history is based on sysadmin history. It was really in a context where I had to manage whole systems with many machines, running many software. And my first question was not necessarily, while now probably it's used for many use cases, but at first it was really not what's the very precise exact consumption of one software in a given context, but what are the trends of consumption of the applications that are running in parallel and that for sure are influencing each other and are influencing how the CPU behaves. But what are the trends of consumption that I could then communicate to product teams with limits, but to start the discussion. And in some aspects, it was not so much for the energy metric. It was because talking about energy rings a bell with the product teams and CSR teams or many people involved with sustainability, let's say, why if you just jump in the discussion with monitoring metrics, so memory, CPU, storage, IOPS, and so on, it doesn't ring a bell. They don't care about this. So it was a way to translate it. So I think what Francois said kind of relates in my head, because for sure, if you want to evaluate in a very precise way what one software consumes, for sure it's very limited. But on the other side of the spectrum, if you are on the system part, at least it was the beginning of the story. So maybe to clarify the positioning, which could explain why in another use case it's also super limited, of course, and you illustrated that very well.
Yes. So there's different aspects in this what you said. So maybe in the sense of the providing a pedagogical value for visualization and being able to explain that yes, indeed, when you run application, you are consuming resources. Yeah, we can hear that there's a lot of value in that. Yes, you can ring a bell that applications, they are running on servers and servers are consuming energy. Yes, that can be an interesting point. The issue that we have. So first, we could say that we could just talk about the energy consumption of the servers and the clusters and the data centers and so on, without going to the level of the application. Would be fair. Maybe it's less pedagogical, but at least yes, it's good from a physical perspective. So there's another question: can we identify trend? It's difficult because we had this discussion with other people that say, okay, maybe in the context of plenty of application running on one server, maybe we can identify trend over the long time. We believe that we took the easy case here with few applications running on server when we can clearly identify the context and so on and so on. And we cannot identify trends here. Can we identify trends, or is it just, it's difficult to see if we are saying real things with those models, or if just the models are stable, but stable in a way that is not representative of the reality. It's a bit philosophical, but I believe it has its impact. If the model is stable over the long term, does it mean that it's indeed identifying the good energy consumption, or does it just mean that it's stable but stable in a wrong way? And it's a difficult question to answer. So yes, so it's not that's not easy to answer. But yes, for sure, we are more interested, Emile and I, in optimization, reducing the amount of servers and so on. And in this frame, we think it makes sense to just talk about energy from the perspective of the servers and just say, okay, for the architects and the software developers, what can we do to reduce the number of servers running? And then it will have an impact on the energy consumption. And the issue of what can we do to reduce the number of servers, I think this is something that can be done with existing performances analysis and so on. Yeah, and obviously, yes. Thank you a lot, Gael, for the hosting of the meeting. Thank you. So that's not yet. That's not an easy question. Because we tend to see that people tend to forget about traditional performance analysis, such as optimizing for either optimizing or considering a frugal design. But optimizing for less CPU, less memory, and so on and so on. So yes, Benoit.
Yeah, on that I agree. For example, in Uber with our clients, we never sell scaffold without talking about resources and LCA and manufacturing impacts and the weight of the applications. Of course, it's just a tool in a toolbox that just could answer some questions in some perimeter of an evaluation. But I totally agree that, and I hope we do a good job in being very transparent about the fact that just looking at power measurement, trying to reduce environmental impacts is very a tiny bit of the question, of course.
Yeah, I think you do. But yes, I think maybe it's a bit, maybe it's seen as less exciting. Maybe it's a bit more boring to talk about CPU and RAM, etc. But I think those metrics still have values because they are actually actionable. You can use debuggers, compilers, and so on.
Yeah. Yeah, they have, and most of the time we cross them with impact estimation, including power metrics. It's just depending on who you are talking to.
Yes.
Yes. It won't lead to any action to talk to them only about IT resources, and it helps a lot to talk about environmental metrics first, but also sometimes power metrics. And it's just about that. But of course, if you don't cross, and these days we are building a stack for evaluation in continuous integration chains, and that's the exact point of focus, to cross metrics from many sources and having side-by-side environmental impact evaluations with IT resources consumption metrics, because without that, okay, it could ring a bell to have the environmental impact assessment, but if you don't share IT resources metrics coming from monitoring tool chains, then you won't be able to say, okay, I should reduce this, or I don't know, put a cache and remove some memory used at some moment or anything. So yeah, of course, it's not something in itself. It's just one part of a bigger answer that should be way more complex.
But yes, as we were saying, if those metrics can help, I don't know, people in the management to make a connection between a program and energy consumption, it's interesting. But yes, we are just raising the fact that there's important consideration when we want to use those metrics for optimization. There's important consideration in how to interpret the results and how to see the results in a broad scale regarding the context and so on. So, but yeah. I think maybe everyone is hungry.
Yeah, maybe I just have a couple of questions, just two questions for you, Dimitri. The first one is, how can Boavizta help you? And do you think that your work can be used by Boavizta in some ways?
So I think, yes, we believe that this work can be used by Boavizta, as I think the Boavizta community uses this metrics of energy, and there's a lot of different projects regarding estimating the energy impact or environmental impact of softwares. We see this presentation as things to know when you are using those models, like things to know in advance to be able to avoid saying things that are false, or important consideration to have when using those models. But we could, yes, we could have a look in how can those model, whose information fits into existing Boavizta projects, where we could fit in this. I think we could put, there's a lot of work with eFootprint, for example, and so on. Maybe this can fit into this.
And just to mention also, there is a project that might converge with your previous work, which it is Energista, because and actually I think it's kind of it could be something that follows what you just presented, which is how could we produce better models in many situations. So when I have physical measurement that's a complete measurement of the power consumed by the machine, but I can't zoom into applications or components, how could we produce models that help with that? And the other side, on the other part, when I have metrics coming from software sensors, but I don't have the full power of the machine, how could I extrapolate to the full power? And those kind of questions, I think, in some way relate to what you did. And the goal of the project is to have so some tooling maybe to collect metrics, some tooling to do stress tests, but more important than just this collection part, a database where we have many samples of data from many different hardware, many different applicative contexts, and then build up on the statistical database up to the point where we could produce models. So it would be very interesting to work with you on that. And there is Adele said he probably would be interested. There is Guillaume Raffin, who is also developing a tool for power consumption measurement, and who is interested in having a more collaborative approach. So if that relates to what you do or what you want to do in the future, I don't hesitate to say, because we would really like to have many people on this project.
We're gonna look at Energista. Yes. We try to do a few things about modeling also. It's quite a tricky question. So yes, maybe there's a good value in working on this together. Okay,
maybe we can wrap up, I think.
Thanks a lot. Thanks a lot,
Dimitri and Emile. It was very interesting.
Yes, it was our pleasure. Thank you.